Okay, this is the last video, station number 9. Visualizing solids. And this is the trickiest part, I think, of the whole unit for everybody. This and naming the IMFs. Okay, look. You got positive, negative molecules here. There's these little dashed lines to show there's this magnetic attraction between the positive and negative. When you see that, and it doesn't specify hydrogen, it does not specify hydrogen, and that's going to be dipole-dipole. If it does specify hydrogen, like right there, then that's going to be hydrogen bonding. In this case, you've got a bunch of positive central atoms, fixed cation, delocalized electrons in a sea of electrons, and that's metallic. Okay, again, this is a different way of showing this. How do I know? Whenever you have this guy right there, the lowercase delta, with the charge, that is a dipole. Delta dipole. Delta dipole. What does a dipole mean? It means it's a positive charge. It's not a formal charge. It's not a complete loss of the electron. In fact, the electron is being shared, okay, between this molecule right here. It's just that it's mostly over on this side, which leaves this side partially positive. Well, guess what? You get a partial positive next to a partial negative. These two dipoles are magnetically attracted to each other. That's dipole-dipole. Dead giveaway that this is different from this. Why? Because there are charges. Look at the difference now. I know this looks very similar to that. I know it does. But this is not, it's different. The reason why is because there are charges here. Whenever you got a repeating positive, negative, positive, negative, positive, negative in a lattice, that's called ionic. That's a salt. That's what all salts look like. They form different shapes now. But table salt, if you look at it under a microscope, it's pretty darn close to a perfect cube. There's a reason why. It forms this lattice structure. Now notice, these are covalent bonds, and these are carbon atoms. They even say it right there, for Pete's sakes. Carbon bonded to carbon over and over and over again is not ionic. It's a network solid, or network covalent. I could take a salt crystal, drop it in water, and it will dissolve. Try doing that with diamond. You think it's going to dissolve? No. Why? Because it's covalently bonded together. Then why does salt crystal dissolve? Well, because you got positive and negative ions that interact with the positive and negative dipoles in water. Let's look at this. Hydrogen interacting with oxygen on a different molecule. Hydrogen from one molecule interacting with the oxygen in water, the oxygen on a different molecule. And when I say interacting, I mean interacting the same way two magnets would interact. There's an attractive force there. That attractive force is called hydrogen bonding. I've showed it to you I don't know how many times. That's what it is, you guys. That's the attractive force. This attraction is the hydrogen bonding. The covalent bonding is what's holding the molecule together. But because the electron's mostly around this oxygen atom, this makes the oxygen, it gives it a pole. The same way that magnets have a north and south pole, it's the same idea. There's this Coulombic electrostatic attraction between these molecules. And we call that a hydrogen bond. Whenever hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine are involved. That's the takeaway concept here. And I know that's tricky. I know it's a lot to wrap your head around. It's not, you know, it's challenging. I get it. Versus this right here. Okay, in this case, This is a chloride anion. This has the electron, which gives it a formal negative charge. This has lost its electron, which gives it a formal positive charge. When these two come together like that, you get an ionic bond. And that repeated over and over gives you a lattice structure. It will give you a lattice structure. That, when you put it in water, it'll dissolve in water. Okay? It'll dissolve in water. Oops. Sorry, that way. Those water molecules just break that thing apart, dissolve. Okay? That will not happen in a network covalent. I don't care how long you put diamond in water, it's not going to dissolve. It just won't happen. It's nonpolar. It's bonded to itself covalently. It'll never ever dissolve. If there's a reason why it takes a long time for sugar to dissolve in iced tea, well, it's because those sugar molecules are being held together. Well, those sugar molecules are not very polar. As a result, they don't interact very well with those water molecules. They're somewhat polar, and eventually it will dissolve, especially if you heat it up. But it takes a lot, it takes a lot of stirring, where if you try to just throw salt in water and give it a quick stir, it's already dissolved. The reason why: salt's ionic. Sugar's not. It's not polar. Or it's less polar. Anyway, these are hydrogen bonds whenever you get oxygen-hydrogen interacting magnetically. That's ionic. You can tell by the charges and the repeating lattice structure of positive and negative ions. That's network covalent. It's bonded to itself covalently. The key point here is it's bonded to itself over and over again in a network. Okay, so those are the key points you got to take away from all this.